All right, hey everybody. We're going to go ahead and get started here. So my name's Shane Kumpf, this is Gian, and today we're going to talk to you about running a container cloud on Apache Hadoop Yarn. It looks like we're still waiting on slides. Thank you. So just a bit of agenda of what we're going to talk about. We're going to give you an introduction to kind of the challenges we've been facing internally, some of the solutions we've come up with there, give you a bit of background on where Docker on Yarn came from, some of the early work, and kind of how that's evolved. We'll get into Yarn native services, which is how you actually run these long-running applications on the cluster, how you submit applications to the cluster, et cetera. A bit about service discovery. So when you have this distributed system with all these containers running on it, how do the containers find each other? We'll do a little demo and then talk about some of the lessons learned. So while we're part of the team, the Yarn R&D team at Hortonworks, that's actually part of the Apache Hadoop community, thank you to Apache, we also have a unique perspective as we're the ones that are running this cluster internally. So we're the operations team as well as the developers on this project. So I think some of the lessons learned will apply to people that are looking to adopt Docker, and specifically Docker on Yarn. And then we'll wrap up with some Q&A. Big disclaimer, right? Some of these features discussed today are still alpha, experimental. There are security gaps. Make sure you're doing your security assessments. This is not yet production ready. Some of these features aren't even part of an Apache release yet. Okay? So with that, a bit of an introduction. At Hortonworks, we build, test, and release open source software, specifically Hadoop and others. The rapid pace of open source means that we're doing dozens of releases a year. Each one of those releases consists of tens of thousands of tests. There's many combinations of tests that we need to run. We have over a dozen supported operating systems. There's multiple backends for things like Hive, think databases, things like Hive, Embari, et cetera. We have nearly 30 open source projects that make up our stack. And we have multiple different versions of HDP that we're shipping at any given time. So as a result, you can see we run a lot of tests. So as we started to talk to customers and look at the industry on how people are addressing these challenges, we've found some common themes. What is happening in the industry? What are our customers asking for? And then internal goals, how can we really reduce the overhead from our existing VM-based system so that we can improve hardware utilization? The common theme, we need to do everything better, faster, cheaper, right? So how can we speed those up? How can we reuse all of this automation we've built to test this software over the last 4 or 5 years as a company? And what we came to find is that a lot of people are gravitating towards containers, right? They eliminate a bulk of that virtualization overhead, which gives us improved density per node. It helps reduce the image variance. We found we have a lot of VMs that have just a couple of changes that need to be in them, right? That's a lot of storage, that's a lot of overhead there. By using composition, right, we can have layers or images that depend on other images in Docker. It really allows us to simplify that packaging and reuse. Container startup is really fast. There's no boot sequence. So as a result, our tests automatically speed up because we don't have to wait for that VM to boot. Containers naturally fit into that Yarn model, right? The Yarn container model, and we'll get more into that. And the big thing for us is this allows us to use what we ship and ship what we use. Because we're running all of our tests internally on this, we get to feel the pain before you do, right? So we get to test all this internally, find where it hurts, and make it a better product. So there's 3 main building blocks to building this container cloud, right? Yarn container runtimes is a new abstraction in Yarn that allows us to bring additional container types, makes it much easier to bring these new services and applications to Yarn. Yarn service discovery, like I mentioned, we have a bunch of containers running across a cluster of machines. We need an easy way to actually be able to find each other. And then Yarn native services is really about an easy API for accessing the cluster, running jobs, et cetera, as well as supporting some of those long-running services, the needs around long-running services. So as a high-level overview of what our architecture looks like internally, this is it, right? We have that Hadoop cluster underneath the covers. It's Yarn, the Yarn native services, HDFS, Zookeeper, and Embari. We actually run Jenkins slaves in containers, in Docker containers on this cluster. Those Jenkins slaves then submit tests into the into Yarn native services, and then Yarn native services works with Yarn to then start up that assembly, start up those containers running across the cluster. So that's a real high level of what this looks like and how we're actually kicking off tests. So, 1 year later, 1.6 million containers, over 300,000 tests have been running on this cluster. It's been a great success, but we've also learned a lot of lessons here. So, having given you a little bit of overview of kind of the direction we went and what we're running, let's go ahead and go a little deeper into the individual pieces here and how we actually made this happen. So, I want to talk a little bit about Docker on Yarn and the evolution there. So, quick show of hands. I don't want to, talk down to the room, but how many people are using Yarn in production today? Excellent. How many people are exploring containers? Excellent. How many people are running containers in production? Excellent. Well, more than I thought, actually. All right, great. So with that context, I want to give just a quick review of what Yarn is. Yarn is the resource management framework for Hadoop, right? There are 3 components in the Yarn stack. There's the resource manager, that's the master. It helps with the scheduling and allocation. There's a per node node manager. This is the one that's responsible for actually launching the containers on a given operating system. And then there's the per application application master, right? The application master works with the RM, works with the node manager to actually request these containers and manage their life cycle. But at its core, Yarn is responsible for managing containers across a collection of machines, right? If we could distill it down. So, as I mentioned, Yarn allocates containers. But what do we mean by a container? It's a very overloaded term at this point. You'll hear about all different forms of containers, from storage to Docker, et cetera. What we meant in Yarn today is really a process, some local resources, the thing like the scripts, the jar file, configuration, security tokens, and then some resource requirements. So that's a pretty simple container, right? That's what makes up the container model on Yarn today. But how does that actually get spawned? And that's where ContainerExecutor comes in. So ContainerExecutor encapsulates that logic on how you start a Yarn container on a particular platform. So the default container executor, that's a script-based executor, runs on Unix and Unix-like systems. From there, Linux container executor came into the picture. This gives you those same features of the default container executor, but it adds things like C groups, right? Some additional security semantics. There's some traffic shaping features in there. And then finally, there's the Windows Secure Container Executor, very similar to the Linux one, but for running containers on Windows, right? So this is really what brings that container to life. Right? You've given it the resources, you've given it the local resources that it needs, the resource requirements, and now this is what's going to bring it to life. So when we started to look at how do we add Docker support to this, the natural way that we'd go is to extend Container Executor, right? And that's exactly what happened. So Docker Container Executor was born, but it had some major limitations. So in the platform today, you can only run a single container executor, right? This now means that everything in your cluster has to run in a Docker container, which might sound nice, but a major advantage of looking to do this a little differently is now we can slowly adopt containers, right? We can continue to have our Hive workloads, Tez workloads, et cetera, running on this cluster natively while we start to move some of these workloads into containers, right? The other big limitation here is all of the goodness that was in Linux Container Executor, things like C groups, now they have to be re-implemented in this new container executor. So as a result, Docker Container Executor has been deprecated, right? And we've looked at a new approach. So what that new abstraction is something called container runtimes. So instead of having a single container executor across the cluster, now we can delegate down to a runtime when we submit the job. So no longer do we have to have just a single approach. Everything doesn't have to run in Docker. This also gives us a nice way to take it beyond Docker, right? While Docker is a very popular containerization framework today, there are many others, and there's going to be more in the future. So this abstraction allows us to then delegate down to that runtime. So the 2 main runtimes today are the default Linux container runtime. This is the existing process-based runtime. So this is just like any container that runs in your cluster today. It's just a different abstraction there. But what we've introduced is the Docker Linux container runtime. So now we can use Docker to actually start these containers using Docker images and then monitor that container through that. So looking at the native support in Yarn for Docker, currently it's handled through environment variables, right? So the reason we chose environment variables, we don't have to change container executor. Environment variables become part of your RPC call. They get passed down all the way, so we could use them there. So it's very easy to just say, I want the runtime type to be Docker, and this is the image I want to run. So here's a distributed shell example where essentially we've told it to use Docker underneath the hood, we've told it to use that CentOS image, and we're going to run the sleep command in there, right? Pretty simple. So having given you a little bit of background on Docker on Yarn, where it came from, and some of the evolution there, I'd like to turn it over to Gian and let him talk about Yarn native services and some of our service discovery work.
Thanks, Shane. So Shane has described all the fancy stuff that we have built for supporting Docker containers on Yarn, and I will describe another very important area that the community is currently actively working on. That's called Yarn native service. So what is Yarn native service? It's basically a container orchestration framework that helps users to deploy, manage, monitoring the containers on Yarn. And the goal of that is, of course, to enable long-running service on Yarn. And when we build this framework, we have these several things in mind. So first, it has to simplify the entire deployment and management of long-running service on Yarn. So it should be very easy for users to bring their existing applications onto Yarn without much manual effort. And also, we should provide some very easy to use tools like REST APIs and command line tools for users to interact with their Yarn deploy services. And additionally, we should provide a declarative way for the user to be able to configure their services, containers, things like how many resources the container require, and also what is the placement constraints for the containers. And lastly, service discovery. If we deploy the service on Yarn, obviously we need a way to let the user easily discover their service on Yarn. So in essence, as I said, Yarn native service is a container orchestration framework that can help you provision Docker-based containers or simply the native OS-based containers. So beyond that, we added a REST API layer that can help users to easily creating, removing, modifying the services in a very declarative manner. So here, I will do a quick demo to show how we actually deploy our HBase cluster on the Yarn cluster with the new Yarn UI. So this is Yarn UI for people who don't know. So, oops. Oh, I got connect. Yeah. So this is a new Yarn UI. So this will eventually replace the old Yarn UI. It has more views, charts, and all the beautiful things. So a quick overview. This is a cluster overview. And the queues, this is a traditional capacity schedule queues, and also the applications that lists all the applications that are running in the cluster. And lastly is the service tab. So I'll use this to show how we deploy a HBase cluster on the Yarn cluster. So I click the new service. So we have two ways. Basically, one is a form-based way where you simply put your service name, the queue name where you want to submit, and the lifetime, all the components that you require. And the other way is just a simple raw JSON format. For the simplicity, I simply just copy and post the JSON format that I have completed before. So this is a HBase JSON format. So I simply, I have to change the name to make it unique. Click deploy. So this will go through the standard deploying process. So while it will take like a few seconds. So while it's deploying, let me quickly walk you through the what's inside the JSON definition. So this is the JSON definition of the HBase app. So it starts with the name. That's the service name you can define by yourself. And the lifetime, so how much time you want your service to be running. If it's empty, it simply runs forever. So as people know, the HBase has two components. One is the HBase master. And it only has one container, obviously. And the artifact, in this context, It's basically the Docker image ID of the HBase container. And the launch command is basically the command that when the Docker container gets launched, here is simply HBase master start. And also the resource requirements, we have CPUs and memories, and also obviously we have to provide configuration files. So we could provide EMVs that will be exported when the command gets launched. And also, most important, the configuration files here. So these configuration files will be made available to the Docker container when the Docker container gets launched. So here, the first one is callsite.xml. So and we can also define the properties for the callsite.xml. All these properties will be localized by the Yarn node manager and made available to this callsite.xml, and that will be mounted to the Docker container. And similarly, we have the HBase site.xml, inside which we will have the list of properties that we want to make available to the Docker container. So similarly, we have another component called region servers, and that has obviously the number of instances you want for your region servers. Similarly, the artifacts, that's the same as the HBase master. It's just the Docker image ID, and other things are just similar to the one that I just described. So another thing is the quick link thing. So this is the service app that registers with the Yarn, so that the user can easily navigate from the Yarn UI to this service UI. So basically, this link just shows the HBase master web UI. So I think the service is launched. So it's called HBase app 26. So I go to this service tab. So here you can see some stats of how it looks like. And for the HBase app, you have HBase master and the region servers. We have specified 1 master and 3 region servers. And we can go into each components and show all the containers for this component. So there's one thing I mentioned before, that's this quick link. So if I click this link, that will redirect me to the HBase master UI. At this point, you pretty much deploy your HBase servers successfully. So one thing I want to highlight here is the URL. Looks like it's still, I'm not sure if people can see. So it's named as HBase master.hbase app.root. The HWX dev.site. So this provides a user easy way to remember where my service is. So the user doesn't need to go to the host, find out the host where the service is running, and then go to their host, and then click the find the IP address and other things. So we just provide a simple way for the user to navigate from their from the Yarn UI to the HBase master UI, the Yarn deploy service UI. So that's that. That's how we deploy the service. And so so that's how we deploy a single service. Sometimes we also want to deploy multiple services together. Think of HBase, it also depends on underlying Zookeeper cluster. So in addition to those, we also provide a way for people to deploy multiple services as a combination from the REST API. So user can reference one service from another service from the JSON definition. And also, user can define which order that they want their services to be started. And they can also define that I want my service to be started until the other service becomes ready. So all these dependencies we can provide from the REST API. And also another important factor is localities. If I have two service containers, so we want to be able to specify the constraints of the placements. By that I mean sometimes we want 2 containers to be co-located on the same host, or we want 2 containers to be separate from each other. Think of the HBase region server. So in that case, we don't want 2 region servers running on a single host. So we provide such advanced scheduling logic in the Yarn core so that we can provide affinity and anti-affinity scheduling. Another important piece is about the upgrade. So once the server is deployed, obviously we want to upgrade them where it's required. So recently we added a feature in the YARN core that's about upgrading the container inputs. So we added an API in the node manager where the user can simply provide the new resources to the container and trigger a restart. So the user basically simply provides the metadata, things like the new binaries, the new configuration files, and the new commands for the container, and then the YARN will take care of all the rest. It will download all the resources while the container is running, and then it will trigger a restart. So one important thing that is, traditionally, if we kill a container, the container resource will just be reclaimed back to the resource manager, and you pretty much have to re-ask the container again. So now we actually avoid those entire process. So we can simply do an in-place upgrade. The container allocation will still be preserved, and your container will be simply restarted with a very minimal downtime because we do localize the jars first instead of kill the container first and then localize the jars. One other thing is left is to hook up this functionality with the REST API that I just described so that the user can do a simple REST call to upgrade their container in place. So that's about how we deploy services. Another important area is about service discovery. How do we discover services on the YARN cluster since it's dynamically deployed and we don't know which node it is? So initially, we implement a feature called the YARN Service Registry. How it works is basically it allows applications to register some information into the service registry, and the other applications can simply look up some records from the registry, things like the IP address, the host name, all those things. So the service registry is based on the Zookeeper. So all the things are stored in the Zookeeper, which provides all the strong consistency guarantees. And also, we provide the Java clients and REST APIs for user to access. So we provide all these APIs for user. However, user still has to change their code, obviously, to use these APIs. That's still not so easy. Hence, we go further. So as many people know that today we have a very widely adopted approach of discovering service just by using DNS. So why don't we apply the same technique here? So if we can allow one application to simply discover another application by the application name itself, it will be a lot easier. Everything will just happen transparently. So what we end up with is a YARN DNS server that's specifically for the YARN requirements. It's still based on the YARN service registry. So the way it works, it registers the listener on the Zookeeper. And anytime a record gets generated in the Zookeeper, it will trigger event to the DNS, and that will correspondingly create a DNS entry. And later on, when the user query comes, it simply respond the DNS queries with these DNS entries. This will enable the use case of like discovering service by application name or discovering service by the container ID. And also, this will work with the standard DNS zone forwardings and zone transfers. Here's how a DNS record looks like. So the first one enables the use case of discovering service by name. It's basically a mapping from the service name to the IP address where the service is running. It starts with the component name .service name .user who submits the app .domain. In this case, the HBase master is the component name, and the HBase app is the service name, and the root is the user who submits the app, and the YARN class.site is the domain name. And similarly, we can have another use case of discover service by ID simply by putting a mapping from the container ID to the IP address. That's that. So Shane will describe some lessons we have learned while we are running our internal Docker workloads in our internal clusters.
Thanks, John. All right. Thank you. All right. So as I mentioned, right, we're working on a lot of the development here with the community, but we're also running an internal cluster, our internal container cloud. So I want to talk about a couple of lessons learned. I will say, some of these might not be best practices, but they're working for us, right? And this is definitely an evolution. We know where some of the gaps are. We're not completely naive on this. So I'm going to talk about how we've solved some of these problems internally with what we currently have, and I'll also touch on some of the things that we're exploring to make this a little better as well. So when you look at Docker, one of the first things, so we've had huge success, right? There's been a huge uptick in adoption. As you can see, our cluster utilization has gone up quite a bit. We've now run over, in the past year, we've run over 1.6 million containers across 300,000 tests. We've now done our first full HDP release end-to-end on this. So our latest release was tested completely on the container cloud, built, tested, and released on the container cloud. We have support for all of the operating systems. And what's interesting here is we run CentOS 7.2 hosts. One of the goals here is to eventually ship this to our customers, right? Make this available for people to use as well. As a result, we didn't really want to make a lot of modifications to the operating system. Many of our customers are using RHEL CentOS, so how could we do as much as possible using that base CentOS install, right? Without any major changes with kernels, et cetera. So we've actually been able to run all of these different operating systems on that base CentOS host. And the big thing is the density improvements, right? When we were in a virtual machine model, we were able to run about 14 virtual machines or 14 tests per machine. Now that we've moved to containers, we've increased that by 2.5x. We can run about 35 tests on a single machine. So again, do things better, cheaper. This is a way we can do it cheaper, get the most out of our hardware. But of course, hasn't been without some pain. So one of the first things that you do when you decide, okay, you've decided you want to adopt Docker, one of the first decisions you need to make is what is the storage driver I'm going to use, right? So behind the scenes, Docker is storing images. It's also storing immutable and mutable layers, right? So we need to store that somewhere on the system. So there's just a ton of different options here, and most of them kind of suck. But what we wanted to do is look at what is the best option for us. Given that we didn't want to make major changes to the operating system, that is the biggest challenge here. We wanted to see what would work great. So we did extensive testing of create, stop, and delete operations, remove operations, to see how each of these storage drivers performed. Because we're going to be creating a lot of containers, right? We're going to create and tear down a lot of containers. So those types of timings are very important to us. If possible, we also wanted to use a driver that was deemed production ready by the Docker community, by those maintainers. So that kind of limits your options as well. Ultimately, we landed on device mapper direct LVM thin pools. Now what this is it allows you to create an LVM-based thin pool. There's devices that are created on top of that. Those devices are now used for your root file system in your container, okay? Out of the box, it uses a loopback file, which we found was very bad for performance, especially when you started to increase the root file system size. When you use the default of 10 gigs, it's pretty snappy. When you need a terabyte to write into that root file system, the teardown of those containers gets quite difficult. So we ultimately landed on this direct LVM thin pool with an ext4 backing file system, or so we thought. So fast forward a couple of months, we've now got significant load on this cluster. We started to do heavy writes in these containers. Yes, there's other ways to approach that via volumes, but for our ephemeral type workloads that we were doing, we didn't want to have to do the volume management for that piece. As people started writing heavily to these root file systems, we started seeing kernel panics. We were losing 2 to 3 machines a day. It was quite painful. We also noticed that there was extremely high I/O weight, right? So we weren't doing a lot of work. We were just sitting waiting on I/O, which really wasn't giving us the best that we could out of this hardware as well. So we went back to the drawing board. What other options are there for storage drivers? Again, keeping that in mind that we don't want to make major changes to the operating system, we found that really device mappers are our only option here. Things like Overlay 2 require mainline kernels. With AUFS, you need kernel modules. Things like ZFS, you have to turn off UEFI secure boot. There's just a lot of challenges, and this is the one that seems to work out of the box. So one of the panics that we ran into, it took some time, but we tracked it back to an LSI RAID controller firmware bug, right? So it's these combinations of your firmware, your Linux kernel, the backing file system, all of this together. So I highly recommend you run some decent sized workloads on this and see what works for you, depending on the OS you do. Ultimately though, we went to installing SSDs. Right? If we back this with SSD, we eliminate that high I/O weight, and it actually goes to nothing. Right? We were spending about 50% of our time in I/O weight before. Now there's almost 0. So we get much better throughput on these disks. Docker doesn't hang because Docker's not completely lockless. If it's doing some things on the back end, things like Docker PS will just start to hang on you. It looks like Docker's not doing anything when really it's hung in the device mapper UDEV communication. So installing SSDs is something I would highly recommend for that Docker graph storage for those backing file systems. Another big challenge is Yarn doesn't manage IP addresses directly. If you think about a pool of IP addresses and the way Yarn works, the resources are managed at the node manager level, a single node level. IPs aren't managed that way, right? They're managed at a network level. And as a result, Yarn doesn't manage those for you. So the way we've addressed this is we've allocated a pool of IP addresses for both our hosts and our containers in the same VLAN, in that same subnet. We then use Docker's bridge networking, a bridge interface connected to that network, and use an option called fix CIDR. What that allows us to do is allocate 64 or whatever number of IPs you want per machine. So now when a Docker container starts, Docker gives it an IP from this range of IPs. In our case, we have 64 per machine. We then use Docker inspect to say, hey, Docker, what IP did you give to this container? We then take that IP and then write it into the service registry that Gian had talked about, and then the registry DNS server picks up that entry, creates the DNS records, right? So this is how we're doing IP management. Again, this is naive. We understand that. We need to support things like overlay networks, more SDN-type models, but for our needs, this works really well. Oops. Another major challenge is user namespacing. So with user namespacing, basically, the user running inside the container, because of the Yarn model, has local directories for logging, right? We also pass in things like containers, those jar files. The UID that's used inside the container must match the UID on the host. When you start using volumes, you run into this challenge. So what we actually do internally, being that we know our workloads, we trust our workloads, we run all of our containers as nobody. We then update our images so that the UID and GID in the image matches that of the host. So on things like Debian, the UID for the nobody user is 65534. Things like CentOS, it's 99, right? If you have a UID mismatch there, you're not going to be able to write files. You're not going to be able to read either. One of the big challenges is there's a feature called user namespacing. It's a kernel feature that allows you to map a user from the host into the container. So map a UID. Unfortunately, the way it works today is you can only remap a single user. So the idea here is you have a nobody user on the outside, but you can actually be root in the container. But as far as the host operating system is concerned, you're still nobody, right? Unfortunately, being that it's only a single user, it doesn't really help us, right? We want to be able to run these containers as any user, but if we can only map a single user at a time, it really doesn't help. There's some work going on to remove that restriction. The restriction is really because when you do that, they actually have to change the ownership of all of the underlying Docker storage to a single user. So I expect as that restriction is removed, we'll migrate to it. We're also looking at things like vanilla containers with no mounts, using tools like Docker logs to get at the logs. But without those mounts, we lose things like log aggregation, some of the great features that Yarn provides. Another is to pass the host UID and then do some user mod chown work, and that's actually in the community right now. Finally is image management. The implicit Docker poll that happens when you do a Docker run can lead to task timeouts. What it looks like to the user is that their task isn't doing anything. It's just sitting there hung. But really behind the scenes, it's pulling down this massive image. The way we've addressed this is we actually run an internal Docker private registry, right? This reduces the WAN load. The first time we kicked these things off, we were pulling down like terabytes of data across the internet. Didn't make the tech ops team real happy. So we have a Jenkins job that actually builds and distributes our images across the cluster instead of relying on this implicit poll. Jenkins also does our cleanup for us because over time, you're going to accumulate images that you don't need. When you're talking about a full HTTP stack, those are some large images. So we have a job that goes out and cleans those up from time to time, which is also a bigger challenge that I'm going to leave for another time. But the content addressable storage model means that two images, while they have different names, could be the exact same data behind the scenes. You delete one, you delete both. So it's a bit of a challenging problem. We reuse our base images as much as possible to reduce that bandwidth, reduce the need to pull it down. And then there's work underway for first-class support of that. So just to kind of quickly summarize where we're at here, we've seen massive density improvements. We've greatly improved the ease of use, a lot of real-world lessons learned, a lot of adoption internally, and self-service. Finally, we'd love to see you get involved. There's still plenty of work to do. We need to do a lot around image management, network plugins, security permissions model, bring your own image. You can check out Apache Hadoop Trunk. build it. I have some Ansible Vagrant setups available if you'd like to do it. If you'd like to follow along, there's the major JIRAs. And with that, thank you. I'd like to open it up for questions. But not you. All right, any questions? Yes.
So what's the key reason so you increase sensitivity from 14 to 35?
Yeah, so there's a few pieces of that. If you think about a virtual machine, it's got a full-blown operating system, right? That has to be started up, et cetera. So there's a lot of overhead as a result. When you're talking the Docker model, we try to get it down to just the processes that need to run inside there. So as a result, we can get a lot better density without that overhead of having, also 14 operating systems running on top of that operating system. Yes?
So the images and all the support, that's distributed to each node?
It is, yeah. So the image has to be local on a node for Docker to be able to use it. So we have to have some distribution mechanism. We are looking at doing it as part of localization now, as a localization phase, so it doesn't look like your task is just hung, right? We do it up front before the task actually gets started. So, yes? So we have. I mean, we've experimented a bit there. There was a talk yesterday about some of the work going on in HDFS around C-block and that. Some very interesting work there that we'd like to try out as well. Obviously, being Hadoop, we have this massive distributed file system behind us, right? If we can leverage HDFS, we'd love to do it. Yes? So the question was, how did we move from a VM-based infrastructure to container-based?
Yeah, both VM-based as well as bare-metal-based clusters to container-based clusters.
Yeah, so, and that was really what we were looking to do, right? Move away from some of the more popular VM management tools to how can we run these containers on Yarn. So it's been a slow progression to get there. We had to build the images, integrate our automation, that sort of thing. Is that what you were going for?
Yeah, and like, is the roadmap to do that, and we have like instructions from the protocols to do that?
So it's not something we've released yet. The question was, is there any instructions on how you actually move from VMs to containers, right? It's not something we've published yet, but I think that's something you'll see in the future, right? It's kind of that journey. All right, I think we're out of time, folks. Feel free to come see me. Thank you.